My name's JP. I'm a developer on Docker Hub, Docker Cloud, Docker Store. I'll be your MC for today and tomorrow. We have a really great group of speakers for you in this track. I am super stoked to see all of the speakers coming through. First off, we're starting real strong with Jason McGee from IBM. So can we give him a big round of applause and welcome him up to the stage?
Thanks, man. Thanks, man. Well, good afternoon. Thanks for coming. We're going to talk today about AI, and specifically about using containers to run AI workloads, and some of the unique technologies that are out there to help you do that, and some of the reasons why Kubernetes and containers in particular are emerging as a really popular platform to help developers build AI workloads. Let's start with why do we care, and why are we talking about this? How many of you have done anything yourself personally with AI, with machine learning frameworks, things like that? Pretty good slice of people. It's pretty clear in the industry that AI and machine learning are approaches that most organizations are looking at. Gartner, in a recent Gartner survey, showed that by 2020, 85% of all CIOs will be piloting at least one AI project. 2020 is not really that far away, which means lots of them are doing it today. And so AI is something that lots of people are trying to figure out, which means lots of us in development and operations roles are trying to figure out how to scale up on AI technologies and how to build out applications and infrastructures that take advantage of AI. One of the things that's really kind of interesting about AI is also that there's a strong tie into hardware and into specialized hardware that's optimized for running AI. AI workloads tend to be very scale out. They tend to take advantage of special purpose hardware. Most commonly that means GPUs. But if you look at GPU technology, it's evolving quickly, and generations of new hardware have massive impacts on the performance with which you can train models and do inferencing. And so you need specialized infrastructure. And this is actually a challenge for a lot of enterprises, because if you go down the route of building out infrastructure to support some machine learning project, you will quickly find that that infrastructure is obsolete really fast. On average, within about a year, the hardware, special purpose hardware, especially like GPUs and specialty AI processor modules, get replaced by the next generation really quickly. And so to me, that says maybe cloud is actually a better place to do this, because in a cloud environment, you don't have to invest in all that special purpose infrastructure. You can use it from a cloud provider and take advantage of those generational changes as they evolve. Now, at IBM, we're doing a lot on AI. And so I want to talk first about what's kind of different about AI workloads as compared to traditional workloads like data workloads, web applications, and APIs. AI looks a little bit different. First is it has a really strong requirement around clustering, the ability to get large amounts of resource, especially for training. You want to be able to take a large data set, spread it across a large collection of resources, and use it to do training. So you get kind of very spiky workload consumption across vast swaths of resource. It also makes heavy use of GPUs and other special processors, which I mentioned. The second thing is you need an ability to scale as your AI workloads grow. And AI workloads grow in kind of two dimensions. They grow from a training perspective. As the data sets that you have to do training with grow, you need more resource and scale to train on larger and larger data sets. And really well applied AI, you're constantly feeding data into your training cycle. So training is not a one-time thing that you do and then never do again. You train, you get new data, you feed that back, and you train again. And so training data is growing, and that causes scale demands. And then on the application side, inferencing, using your models, obviously as your applications grow, you're doing more and more evaluation against the models that you built to serve up meaningful results to your users. And so there's really high scale demands around AI. And then the third thing, which maybe is less obvious for people as they get started with AI, is the importance of security and isolation in AI applications. In a lot of cases, especially in enterprises, you're trying to do machine learning on sensitive data, on customer data, on financial data, on information that you consider strategic to your company. And so it's really important to be able to apply machine learning in secure ways on secure infrastructure, because you're going to use it to gain critical insights against sensitive data that you may have inside your company. Now, at IBM, our AI work is centered around Watson. Most people have heard of Watson in some shape or form. And Watson, for us, is a couple of things. Watson is, at its base, a set of APIs around machine learning and artificial intelligence that we make available to you. So I think of this space as kind of 3 layers. There's the base frameworks that you need to build your own models and to do machine learning. And in Watson, we have things like deep learning as a service that allow you to easily create your own models and do training. But for a lot of developers, you don't want to kind of start at ground zero and go figure out how to build a neural network model to train on some data set. You just want to add intelligent image recognition to your application, or you want to build a chatbot that understands natural language and lets you interact. And so you want APIs that are already trained models that you can easily consume. So we've done that in Watson as well. We have a 30+ APIs that we expose through IBM Cloud that allow you to do natural language processing, to do image recognition, to do chat and conversation, to do data discovery, to do trade-off analytics. And those are specific models trained on public data sets or data sets that we have that you can then delta train with your own data to specialize them for you. And so we provide those APIs. And then at the top layer is kind of AI applied to specific problems. Like we've talked a lot about Watson Oncology, like where we've applied the ideas of Watson machine learning to the domain of cancer research to help doctors do a better job building treatment plans for patients around cancer treatment. If you look at the Watson team, they have to build all of this infrastructure. So they are AI and machine learning practitioners. They're building models, they're training data, they're building this catalog of services, and so they need a way to do that and an infrastructure on which to do that. And they've been doing Watson on containers for a long time. And so as we at IBM in the cloud team looked at our support for Kubernetes and containers as part of our public cloud, we actually used Watson as one of the driving workloads to design that infrastructure, to design our container service, to design our cloud infrastructure, to really tailor it for running AI and machine learning workloads. And we've learned a lot throughout that journey about how to use container infrastructure successfully to run these kinds of workloads. And just to give you a sense of scale, this is not the total scale of Watson, but just to give you a flavor, there's about 12 Watson services running on Kubernetes today, live in production on our public cloud. That's represented by about 800 services within Kubernetes. Just in one deployment, we obviously, since we run a global public cloud, we run all over the world in many regions and availability zones. If you just took one piece of that, just to give you a sense, one deployment of one of those services is about 500+ physical machines with over 3,000 pods running on it that we're using to host Watson. So, we're doing this at reasonably high scale globally around the world. So what I thought I'd do today is kind of share some examples of how you can use Kubernetes to run these kinds of workloads, and how cloud-delivered Kubernetes gives you the best platform to be successful at that. So let's get started and talk a little bit about open source deep learning frameworks. One of the really exciting things I think in the industry right now is there's tons of activity in the open source community around frameworks to help you do machine learning and deep learning. And some of those frameworks are focused on how you represent the training job, build the neural network models. Some of those projects are focused on how you actually do the computation and spread that computation efficiently across a set of resources and take advantage of GPUs and specialty processors. And some of those frameworks are focused on how you as a developer can write your training jobs and leverage cloud infrastructure like containers as the platform to do that. And so what I'm going to do is take you through one example. There's a number of interesting projects in this space. At IBM, we've been building a project called the Fabric for Deep Learning, or FIDDLE. and this is a framework that's really designed to help developers build AI training jobs that leverage Kubernetes as the platform. Now, if you look at the kind of stack of technologies that you tend to use to build out a machine learning application, at the base, of course, you have physical infrastructure, including specialty hardware like GPUs. On top of that infrastructure, you need an abstraction layer to run computation, which is Kubernetes. Kubernetes deployed in a way that can take advantage of all of that infrastructure. On top of Kubernetes, you have a whole bunch of popular frameworks, TensorFlow, Caffe, PyTorch, Keras, that all help you to actually build out the models in your training jobs. And then Fiddle comes along as an orchestrator on the top to help you orchestrate the training jobs to scale and take advantage of the resources. So another way to look at it is like this. And we're going to kind of focus today. I'm going to show you a little bit of a demo of how to do this on those training jobs at the top. So infrastructure in Kube is the base platform. How do you, as a developer, write a training job and take a cluster managed by Kubernetes and use it to scale out and run those training jobs? If you look at the architecture of Fiddle and kind of the pieces that we're putting in play here, it looks like this. The box in the bottom left is the Fiddle framework itself. So this is orchestration. It gives you an API to submit training jobs, to spin up resources, which is the picture on the right, a pod that is a collection of training pods that are running your training code. Those training jobs are using frameworks. So in the example we're going to walk through today, we're going to use a few of the other popular open source frameworks as part of how we do this training activity. And so Fiddle provides the kind of orchestration layer on top of containers to allow you to manage training jobs and scale, and then take advantage of the actual frameworks to do the work. So let's walk through an example. So this is the basic flow we're going to walk through. Obviously, if you want to run a machine learning workload, first you need a container environment. I'm going to skip that for now. I'll show you how to do that later. But you need a kube cluster environment to run on. You need Fiddle running on that kube cluster. That's easy. That's a simple Helm chart deploy to install all of the infrastructure needed to help you manage machine learning jobs on Kube. Then you use that environment to run training jobs, to collect results, and then to serve up that application in the end. For this example, we're going to actually build a visual recognition training job. It's basically going to allow us to take images of clothing and determine what that clothing is. The data set we're using for this is a public data set called Fashion MNIST. It's a collection of 60,000 images of clothing items, plus a 10,000 image test set. So the idea is you use the 60,000 images to train the model, and then use the 10,000 images to test the model against the training. And these are all provided in a standard format that allows us to build a meaningful model around clothing. And once you train the model, the idea is you can feed it a picture of any other kind of clothing and it'll tell you what it is, right? This is the basic structure of the model that we're going to build. So it's a 5-layer neural network model. It uses Keras, the Keras project, as the way to define the training job itself. It's written in Python. It's a Python framework. Keras, that model definition, then gets processed using TensorFlow to do the computation, and orchestrated using Fiddle, all on top of Kubernetes. Right? So those are the 3 kind of layers that are brought together. In the end, what we're going to get is a model, and then we can use that model to build an application that can take images and tell you the results. And so we built a web application. We used a project called Seldon. Seldon is an open source project that we're working with now that's really about how you build applications that use models. So it's not about training, it's about using. It's about running inferencing. How you build applications that actually use models and run them in Kubernetes. All right, so we built a simple web app here that lets us upload images, and it'll build a word cloud of what it sees in all the images that you've selected. All right, so let's take a look at this. Let's see if we can start. So for this example, of course, I'm running on IBM Cloud, my kube cluster on IBM Cloud. I have a cluster already up and running. Just to give you a sense, assuming I haven't logged out here, of how easy it is to spin up new clusters. So if I wanted to build a kube cluster with GPU support to run a workload like this, I can simply come in and say, create me a cluster. I can actually do clusters that are multi-zone, so I can spread my workload across zones. You know, when you're a developer just getting started with building a machine learning job, you're probably not thinking about scale and availability, but eventually you're going to do this in production, and you want to do it with scale and with high availability, so you want a multi-zone deployment. So that's really easy. You can just say, I want 3 zones, and we'll distribute kube across it. I pick a kube version. I always like to run the latest. And then I pick the infrastructure I want. And in this example, I'm actually going to run on bare metal compute. So I want containers running directly on bare metal. I want the full horsepower of the system. I don't want any virtualization in the way or any overhead, because I want to really be able to exploit this infrastructure to run my jobs. And I want systems with GPUs on them. So I'm going to pick these flavors, which are 16 core, 128 gig bare metal servers with GPUs. I specify the number and a name, and I hit click to create, and I get a cluster. It takes a few minutes, so I'm not going to make you wait. So we'll just go to the cluster I have. So this is the cluster I already have running. So this is a fully multi-region deployed Kubernetes cluster, 6 workers, 2 in each zone, all GPU-enabled machines. If you look at the flavors here, you can see these are all GPU-enabled machines. So I have infrastructure, Kubernetes infrastructure, to do this work. All right. Now, how do I actually go about training? So what I'm going to do is I'm going to kick off a training job on this cluster. I'm going to pick a base model and a definition of the job that I want to run, and go submit this job. Now, what's going to happen while this is running is I'm going to spread this job across a sequence of workers in that cluster. If you want to look at the definition, let's go look at the definition here. So this is the manifest that I just ran. Can everyone see that okay? Can I go a little bit bigger? You can see what we've done here is we've said we have a job. It runs on GPUs, uses 8 CPUs. So each learner, each pod that's doing training uses 1 GPU and 8 CPUs to do the work, and 16 gigs of memory. It's using a that data model that I talked about, those 60,000 images, sitting in object storage. So it's pulling the data set from object storage. And then it's using TensorFlow to execute a training job that's written using keras in this Python file, right? If we won't go through the gory details of it, but if you look at that Python file, this is actually the definition of how to do the model training, right? The actual code that you're writing to build the neural network model. So it's basically automatically kicking off for me a TensorFlow execution on a collection of containers running in the cluster. I actually ran this already with no GPUs. So just to give you a sense for the impact you can have, I've run the same model previously with just CPUs, so 30 CPUs. And if you looked at this, the results of this, you can see it took about 10 minutes for this data set to train the model, right? And when the other one finishes, you'll see with GPUs, of course, it goes much faster. And you can, from Fiddle, you can get some metrics that kind of tell you how good this model's doing. You know, with AI models, the key is increasing confidence, right? You want to have higher confidence scores in the model, so as you feed in new data, that the results get better and better. And there's a number of metrics you can look at to get a sense for kind of how good the model is doing against your objectives. Now, we'll let this run. It takes about 5 minutes for the training job to work on GPUs, right? So we get about a 2x speed up in this example for this data set by running on GPUs instead of CPUs. So Fiddle is kind of orchestrating this for me. If I go look from a monitoring perspective, in this example, I'm using Sysdig, which is a company we partner with as part of our ecosystem to monitor that cluster. And so you can see this is actually the CPU of all the nodes in that pool. And you can see right here this big spike in CPU on this worker as it started to crank through a particular training job and process that within the cluster. So while we let that run, when that finishes, I wind up with a model. And that model allows me to understand new images. So here's a set of images. They're not part of the MNIST data set. Right? That data set, if you were paying attention, was all black and white images that were designed specifically for training. These are kind of random images of clothing that were already loaded. And you can see this is what it thinks they all are. And I can upload something new. So if I go upload something else like this red shirt, I can add that into the model. If it, oh, yes. Thanks, Nylash. It helps if you hit submit. There we go. So you can see I uploaded this new picture. It thinks it's a t-shirt and a top, and you can see the confidence scores at the bottom there of how confident it thinks it is. It's 100% confident it's a t-shirt, and 0% confident it's a boot. That's good. Guess it got that one right. It's also 0% confident it's a shirt, which is interesting. See, you always have to evolve your models. And so that's the idea with this example, is that it's easy for you to build these models. As a developer, I just built the model definition in Python. I could then easily submit that model to Kubernetes and let Kubernetes manage all of the resources needed to process that model and to store the results back in object storage. And I can kind of iterate through this easily. I showed you a simple web interface to Fiddle to do this. You can, of course, do this on the command line, so you could do it as part of a pipeline or as part of a iterative process where you're kind of constantly evolving the model and retraining. All right. And that finished now. And if we go look at that model, you can see this took a little under 5 minutes for that to train with GPUs, right? And that's one of the nice things about this framework as well, is that you didn't have to change anything about the definition of the model. Like, I can simply reconfigure in the manifest whether I want to use CPUs or GPUs, how many I want to use, how much resource I want to throw at it. And the framework takes care of exploiting that across Kubernetes. All right. Let's pop back here. Okay, so that was a simple example. You can do other things. There's other projects, of course, that are in this space. There's projects like Kubeflow, which also are attempting to provide an open source framework for doing this kind of job execution and coordination on top of Kubernetes. I think the short answer is this is becoming the platform that everyone's using to do AI machine learning workloads. And I think that's really interesting. I mean, this is what, year 4 of DockerCon. In previous years, as we talked about the container space, most of the workloads that we were talking about were much more stateless workloads. Web applications, API backends, mobile backends tended to be more kind of stateless scale-out workloads. And here we are today. We're running data-intensive applications, big data and analytics jobs, machine learning, databases. There's a lot of really interesting, deeply stateful workloads that we're able to execute in a platform like Kubernetes as well. Now, you're a developer, you want to go do this. Why do this on a public cloud? What are some of the advantages and some of the other things that you should be thinking about when you build these kind of workloads yourself? And I really think that public clouds, especially managed services like managed Kubernetes services within public clouds, really are the ideal balance. They give you access to resource and special technology, and they reduce the burden of you having to spend all your time building infrastructure to support these kinds of applications. And at IBM, as we thought about our whole cloud overall, we really thought about all the layers of cloud that are needed to be in place to really run AI well. And we've optimized a lot of our core stack around that. At the base, we have our core infrastructure, and we've populated that infrastructure with high-speed networking, with large memory and CPU machines, so you have a lot of horsepower with GPUs and various generations of GPUs to give you access to the raw infrastructure you need to run these kinds of workloads. We just spent a few minutes looking at the container layer in Kubernetes that sits across that infrastructure and gives you easy access to deploy and run jobs on that infrastructure. And then as you go higher up the stack, you think about data, you think about the Watson APIs that I talked about. All of these things come together to give you the collection of services you need to be successful, building your own models and using AI as part of applications, which is ultimately what we're all trying to do. Like, AI is an interesting scientific domain, but it's really interesting for all of us because we're trying to figure out how to build these capabilities into apps that we're delivering for our customers. Now, if you think about Kubernetes in particular, why it's good, obviously one reason it's really good for this is the vast collection of frameworks that are now available to run on Kube. I mean, I mentioned like 6 of them in that simple demo. There's a lot of activity in this space around being able to run deep learning frameworks on Kube. The abstraction of infrastructure, I think, is the other key value prop in Kube, is that you don't have to think about the infrastructure. You can let Kubernetes take care of that and focus a little higher up on your code and on your applications and taking advantage of that infrastructure to get meaningful work done. AI is also moving quickly. Like, frameworks are coming out all the time, hardware is evolving. You need an ability to keep up. Like, the way you solve a problem using machine learning today will be completely different than the way you solve it 6 months from now, because it's a space that's everyone's learning very rapidly. AI in general is a domain that's been talked about in computer science for decades. It's only really in the last 5+ years that it's really taken off, and I think that directly coincides actually with cloud and with the ability to have access to this kind of resource to be able to apply to data problems like AI. And now it's being delivered in a way that all of us, even if that's, we're not experts in this space, can take advantage of it. I think the other reason that cloud is good for AI workloads is because of the things around it. Like, you can build tool chains to do DevOps. You can do things like rollouts and rollbacks and make changes quickly in the environment. You have simple deployment models for things like Helm and even just kubeyaml by itself. And so a lot of the other problems that you have whenever you do any kind of software development also apply to AI workloads. And so you want an environment that solves those things for you. At IBM, our container service is called the IBM Cloud Kubernetes Service. It is a managed Kubernetes service. So it tries to take that base layer that I showed in that architecture of a Kubernetes environment and just deliver it to you as a managed service. You do not have to worry about how to provision Kube. You don't have to worry about how to secure it. You don't have to worry about how to scale it and keep it up. You can do multi-zone. You can get high availability. You can add resource to it. And all of that is automated and not something that you have to worry about as a user of a service like IKS. We run the Kube masters for you. We take care of all the infrastructure provisioning and management for you. We do health monitoring and recovery if things were to fail. We give you the operational tools that you need to manage that environment. And we can do that globally. We can run that all over the world, right? And that's really important when you think about things like privacy regulations, data sovereignty rules. You have to be able to do these things. If you're going to do AI on data, there's rules about that data. Who can touch it, where it can live, where it can go. You need a flexible platform that allows you to stay within those rules. As I thought about this problem, I thought there's 3 or 4 kind of really key attributes of Kubernetes via our cloud that I think make it really well suited to running AI. One is a high availability. Right? The ability to have AI applications, both training and inferencing, that can run with high availability. If any application that you build that you're going to use in real life, you're going to have to deal with, how do I keep this thing up? How do I either enable my team doing training to have a reliable environment to do that training in, or how do I have my end users be able to serve applications? So you want a highly available environment. We just recently announced support in our container service for the multi-zone features that I showed you briefly during the demo, where we can automate the provisioning of Kubernetes across multiple availability zones. We spread the workers for you. We label them appropriately so the Kube scheduler can automatically distribute your application workloads across zones. We set up the networking that's appropriate between the zones. We set up global load balancers to do traffic distribution from the internet across those zones with smart health checks. And we take care of all that for you, right? So you don't have to worry about how to set up that kind of infrastructure. And so I think multi-zone deployments for high availability are a critical capability you want to be able to exploit whenever you're building these kinds of applications. Second thing is obviously scaling, the ability to quickly scale and add resource. AI workloads are fundamentally designed to horizontally scale and to be able to take advantage of lots of independent compute resource. You want a way to do that quickly. In this example, I provisioned a relatively small cluster of only 6 workers for the purposes of showing you that demo. But in a real workload, you might provision hundreds of nodes to do training. Some of the Watson workloads, we're doing training on 800 or 900 node GPU bare metal clusters to do training on large data sets. And you can spin that up and do training and then tear it all down when you don't need it, because obviously it costs you money, and scale easily the environment to handle these kinds of workloads. Access to specialty infrastructure, I think, is the third thing. GPUs are where we are now, but there's other technologies. There's special silicon that's multiple companies are developing for machine learning workloads. There's special hardware happening at the network layer to allow very high-speed interconnect between components within the cloud, so you can do data sharing within models. There is even CPU design that's starting to change to be more optimized for the kinds of use cases we see with AI. And that stuff is easier for everyone to consume in a cloud context because we can bring that into a cloud, we can make it available to a large collection of people, and you can take advantage of that specialty hardware. The extreme of that is even things like quantum. You think what's going on with quantum computing. At IBM, we've actually made some very early versions of quantum available through the cloud, right? Those are not about production workloads. That's about us all experimenting with what do applications on quantum computers look like. But there are use cases where we think things like quantum will apply to AI, and via the cloud, that will be really probably the first place all of us can get access to that kind of technology and use that as part of how we solve some of our problems. So I think tailored infrastructure via cloud is a really important value prop. And of course, with containers, it's easy to then use that tailored infrastructure. I didn't show it to you, but in the case of this Kube cluster that I deployed, since it has GPUs, Kube has been configured with extensions for GPUs. So Kubernetes knows about those GPUs, and containers can take advantage of them and allocate them. You can do scheduling based on them. And that kind of abstraction is really key as well. The next thing, I think, is the broader catalog of services around your application. I showed a simple example of building a visual recognition model. Maybe there's a reason why you wanted to build that yourself. But in the application you're building, you might also want to do natural language processing. And you don't want to have to build every model yourself. You want to be able to focus on building specific deep learning models around domains that are of high value to you and using deep learning models in places that aren't high value to you. And so doing this work in the context of the IBM Cloud means you can run these models on Kubernetes yourself, and you can take advantage of the services in things like Watson or in blockchain or other services in the catalog to compose the total application that you want to build and really focus your energies on the parts of the problem that are worth your development investment versus using services directly. The next thing which I think is really important is security. We spend a lot of time at IBM in our cloud services focused around security. As I said in the beginning, machine learning applications tend to process sensitive data. So you need a stack that allows you to build out a secure infrastructure to run those workloads. I think security within containers happens at many layers. There's security within the delivery of the software itself. So how do you safely store and distribute images? How do you do signing of images so you know what you're running? How do you do things like vulnerability scanning of both images, the packages that are inside of images, and also the configuration of the software inside your images? Package vulnerabilities is one thing, but a lot of insecurity in software actually comes from how we've configured that software. You have weak password rules. You have the default passwords in place. We all do things that we're lazy or we forget, and we deploy software that's insecure. You want to get visibility into that. So the first piece of security kind of starts at that image layer. The next layer of security is the runtime itself with Kubernetes and the hosts that Kubernetes are running on. So how do you actually secure and lock down the hardware and the operating system? How do you protect the network coming into that cluster? How do you do monitoring of that environment? I showed you a quick snapshot of Sysdig for doing monitoring. But you really need deep visibility into an environment to understand how things are behaving and whether they're secure. And so we've done a lot in our service to, out of the box, build a very secure container environment where the host, the network, Kubernetes itself, policies are all set up in a way that give you the best default security out of the box for running your workloads. And then the final layer, which I think is emergent, is Istio. How many people here have heard of Istio or played around a bit? Pretty good visibility. Istio, I think, is the next big wave that's happening this year. in the container space around the interconnections between services that you're running on Kubernetes, and how do you get visibility between microservices, how do you secure the communication between those services in a way that's agnostic to the infrastructure. I want to say service A can talk to service B. I don't care where they run. I don't want to deal with network CIDR blocks. I just want to talk in terms of the application itself. And so all of these things come together to give you a secure platform for running applications, including AI applications. And I think they're really critical that you have a secure platform when you're doing this kind of work. So those are kind of 5, I think, key attributes of a managed Kubernetes environment for running AI that make this a better place to do that kind of work than building out infrastructure on your own. So to wrap up, and then we can do some questions, IBM Cloud Kubernetes Service is the place where we're doing this work. We continuously evolve the service that we make available for you to run Kubernetes on the cloud. Our team actually does, last time we checked, on average about 50 updates a day to our service globally. So we have pretty high velocity. We're constantly delivering new things, some of which we didn't even talk about, like trusted compute. In the context of AI, I think our recent support that we added for bare metal GPU worker nodes, which I showed you, is really key to allow you to run machine learning workloads. Multi-zone clusters is really key for availability. Istio is emergent for securing applications. And then we continue to expand the ecosystem of partners with people like Sysdig for monitoring or LogDNA for logging, which give you the tools to use with your applications to help you get visibility into the operational behavior of those applications. And with that, we have a few minutes to do questions. Any comments or questions from people? Yeah.
Hi, my name is CJ, ex-IBMer. It's surreal watching you talk about this, knowing you from WebSphere 3.0.
My old life,
yeah.
WebSphere.
The question I had was regarding the manifest. At one point in the manifest, you did specify how many, what kind of resources you had available explicitly.
Right.
Wouldn't it, just asking out of curiosity, wouldn't it be better to use a label or a node selector, allowing you to then, or like you pointed out with the Istio spread, make it more agnostic so that you don't have to explicitly specify.
Yeah, so you're talking about, just to be explicit about it, you're talking about this right here at the top, right? So first off, so the question is there a better way to represent these kinds of resources that's more selector label oriented within Kubernetes? And the short answer is, first, there's room for improvement in how these things are specified. The idea of this was, what are the resource requirements of the job, of an individual training job, not the total resource requirements, but for an individual job, it's going to consume this. Think of this more as like resource requests in Kubernetes, where you give some hint to the scheduler about how much you need. One of the challenges, I think, with all of these frameworks is how much of Kube do you show through? Like, who's your audience? The audience of a manifest like this is a developer or a data scientist who's trying to do machine learning, and maybe they don't know anything about Kube at all, or they have very low skills, so they want a simple representation of their job. I think that line is very fluid. There's lots of projects that are trying to abstract, and it might be better to just teach everybody the base things. With the evolution of custom resource definitions in Kubernetes, we're seeing more and more stuff be manifest directly in Kubernetes YAML language. So I do think there's some room for improvement here, but it is trying to kind of abstract a little bit that infrastructure and have a simple specification of this is about what I need for this training job to run, and let the framework handle it under the covers. When you say things like GPUs there, that does fiddle under the covers, does then do things like put the right labels and taints and tolerations in place to ensure that this pod only runs on worker nodes that have GPU support in the cluster. And so it is causing Kubernetes to do the right things under the covers. Any other questions? Yeah, yep.
So I have a question about the way that you're moving data. Hello? Can you hear me?
Yeah.
Cool.
It's on.
Yeah,
Yep.
great. So my question is about moving data into the containers which are running the training.
Yeah, right.
And I saw there that you had an interface for doing so, but I guess that's something that's specific to what you were doing. So typically, you set up a Kubernetes cluster and you have some job in Python or whatever that you want to do, and it has some training data, and you might get that data from an email or something, and you just got an email. It's like, oh, here's the data, and you get your data, and then you want to put it into that model, or you want to put it into that container and run it.
Yeah.
There are a lot of different ways to do that,
There are.
and currently I haven't really found one that I found to be like, oh, this is the way I like it. And maybe it just changes depending on the circumstances.
Yeah.
Very much could, but I was wondering what your thoughts are on that.
Yeah, I think you're right that there's a whole part of the AI domain which is like, how do you get and prepare data for training? In this example, I wound up using object storage as the input source and the output for the training jobs. So all the data was kind of collected there first, and the job pulled data from object storage to do it. That works for some things. For other applications, you might have to come from databases or do multiple things. We actually have a whole set of tools which are just about basically building like a data factory to take data, to refine it, to, sometimes you want to cleanse data, like take certain fields out of a database that you don't want to show up in the model. I think the reality is there are a lot of ways to do it today. There's not a good way. There's a few common patterns like object storage, which you see a lot of. How you do it depends a lot on the problem you're solving. In your case, if you did something like training on email data, what most people would tend to do is forward the email data off to a big data set in something like object storage and then train on that big data set. In other cases, you're going to pull from live sources as you do training. But it's a big kind of, I wouldn't say unsolved, but solved too many times problem in the space that there's room for simplification of kind of data wiring between things. All right. Well, thank you for taking the time. I'm up here if you have any other follow-up questions. Thank you.